Hello everyone, welcome back to my channel. So in today's video we are going to be learning about binary search, and I know I've been away for a while, but I'll try to post videos more regularly from now on. And yeah, if you like this video, please don't forget to press the like button and subscribe to my channel. It would mean a lot. Press the notification bell so that I get notified every time I put up a new video. And yeah, also I've noticed that a lot of you haven't subscribed to my channel, so please do, it will mean a lot. Okay, so with that, let's begin with the binary search. Okay, so let's talk about searching first. What is searching? So searching means looking for a particular element inside a data structure, right? Let's say we have an array 2, 3, 4, 5, 6. Okay, and we are looking for an element 4, right? So when we look for an element 4, we are looking for an element 4. As soon as we find it, we return it. Okay, we return the position or we return the element, right? So that is called searching. Searching means looking for a particular element in a given data structure. Here the data structure we are talking about specifically in binary search is array. We will talk about why we are talking about arrays and not any other data structure. So now let's talk about binary search. Why is it called binary search? And what is the difference between binary search and linear search, right? So the most popular type of searches we know is linear search and binary search. So in linear search, what happens is we compare the element to the given value to every particular element in our data structure. Let's say we have been given this value 4 to search for, right? And if this is an array, what we do is we will start from the 0th index and we will compare 2 with 4 not matching, then we will increment. Okay, then it will compare 3 with 4 not matching, then next value, then 4 with 4 matching, return 2, right? So this is how linear search works. Let's say if you want to search for 6, then 6 is again not matching with 4, so then we increment the pointer, and then again what happens, 5 is compared with 6, then again not found, then 6 is compared with 6, then it is found, then it is returned. Okay, so this is how searching, or I should say linear search in particular, works. That it compares the elements with all the particular elements in the data structure, and that's why it takes more time. Okay, so what is the difference between binary search and linear search? Linear search takes order of n time, which means time proportionate to the number of elements or to the size of the array, which means the time taken is a lot more. In case if we have 1000, like n is 1000, then time will be proportional to 1000, right? So that is what is linear search, that is the amount of time linear search takes. However, if we talk about binary search, it takes significantly lower time, as we will see later in the video. It takes this amount of time, log n time, right? So the time complexity significantly reduces in case of binary search, so we use binary search wherever we can use it. Okay, so what is the salient features of binary search, or why is it called binary search in the first go? So it is called binary search because what it does is in every iteration of the algorithm, it will divide the search space into half. Okay, so what it will do, it will divide the search space into half, means if we have n elements, let's say in the beginning if we have n elements, then in the next iteration it will make it n by 2, the search space will reduce to n by 2, then next it will reduce to n by 4, then n by 8. So what it is doing is it is significantly reducing the search space in every iteration. Where in case of linear search, what keeps happening is, if you have read about linear search, what happens is every time the search space reduces by n, by 1. Okay, so if it is n, then in next iteration n minus 1 elements it will search for, then in n minus 2, then n minus 3, and so on, right? But in binary search, it reduces the search space by half in every iteration. That's why the time taken is less, comparatively significantly less as compared to linear search. Okay, so but there are conditions where we can apply binary search. We cannot apply it to any given data structure. There have to be certain conditions that need to be met in order to be able to apply binary search. What are those conditions? So let's talk about them. One thing is that the array needs to be sorted. Sorted array. Okay. In case of linear search, that's not the case. Even if it is 8, 2, 1, 3, 4, we can still search for 4 in the array, right? But binary search won't work on such type of arrays. Okay. Binary search only requires sorted arrays, either ascending or descending. Okay. So one thing is it works on sorted array. And why am I specifically saying array and not any other data structure is because one of the most significant requirements of binary search is that their data structure should be random access. Okay. The data structure should be random access means it should take order of 1 time to access a particular element in the data structure. If it is not random access, then the time taken will not be order of log n. Okay, in order to reach a particular element, it will take more time, right? We'll see all of this later. If you are not getting it, it is fine. Let's first jump into the algorithm. I've given a lot of introduction without going into the algorithm. So let's start. Let's first go through the algorithm and an example, and then we will see why it works, why we have these conditions and how it works. So yeah, let's begin. Okay. So what does this say? Let's say this is the array that we have. I'm writing the indices here. Okay. So we have 10 elements in the array, let's say. So what is the algorithm doing? It is not in any particular programming language. Okay, it's just an algorithm. So it's a pseudocode. Int binary search, it is returning an int. Array, we are passing the array beginning, end, and x. Beginning means from the starting index from which you want to search, end index, and x is the element that we want to search for. So what it is doing? While beginning is less than equal to end, what you do while beginning is less than equal to end means search space has some elements. Okay, if beginning is greater than end, it means that there is no element to be searched for, practically speaking. Let's say beginning is here and end is here, then it means that the search space does not contain one or more elements, right? So beginning should be less than equal to end. You will see why is it this condition. Then mid is equal to beginning plus end by 2. What it is doing, it is calculating the mid index. Okay, depending on the beginning and end, it will take beginning and end and divide by 2. Then if array of mid equal to x, what do you do? If array of mid, yani ki if the middle element is equal to x, right? If the middle element is equal to x, then return mid. Return that particular index that we have found, this particular index element at this particular index, then return the index. Otherwise what you do, else if array of mid is greater than x, okay, array of mid, let's say this, okay, if array of mid is less than x, greater than x, if it is greater, what you do, you reduce the search space here, okay, otherwise you reduce it to here or you go into this, okay. So what is these two conditions are doing? If it is middle element is our element that we are looking for, if it is found, then done. Otherwise what to do? Otherwise you reduce the search space. What you do? Either go in the left hand side or go in the right hand side. Okay, either left or right. What it is doing, either beg is equal to mid plus 1 or end is equal to mid minus 1. And if this loop is ending, okay, no mid is found and the element is not found, then return minus 1. Okay, now let's iterate through the loop and see the example. If you haven't understood anything till this point, no problem. Let's go through this example, you'll understand. While beginning is less than equal to end, let's say this is the array, okay, beginning is equal to 0, that is the 0th element, and end is equal to 9, and x is equal to 23, that is the element we want to find. Okay, so while beginning is less than equal to end, beginning is less than equal to end, it is, then mid is equal to beginning plus end by 2. Now what is mid? Mid is equal to 0 plus 9 by 2. So what is this? 4. 4, okay, integer division 4. So now mid is equal to 4. Now mid has become 4, beginning was this, and end is this, right? maybe I'll write here. Okay, done. Now what is happening? If array of mid equal to x, array of mid is what? 16. Is 16 equal to 23? No, right? 16 is not equal to 23. Then what should we do? 16 is not equal to 23. Then this condition fails. If array of mid is greater than x, array of mid is what? 16. Array of mid is what? 16. Is 16 greater than 23? No, it's not. Then skip. Else beginning is equal to mid plus 1. Beginning is equal to mid plus 1. So mid is what? Mid is 4 and beginning is equal to mid plus 1. Mid plus 1 means 4 plus 1 is 5. Now beginning is this. So you saw how the earlier beginning was this, end was this. So search space was this. Now what is happening? It is saying now it has done some comparison, constant time comparison, and now it is saying that we have to search here. Beginning is equal to mid plus 1. We have to search here. Now the search space has reduced to this. Okay. Now let's move forward. This is done. Now again beginning is what? 5. End is what? 9. So 5 plus 9 by 2, 14 by 2 is 7. Okay. So mid is 7. Okay. Mid is 7 now. Mid is equal to big plus n by 2. Okay. So 5 plus 9 by 2, 7 we got. Now if array of mid is equal to x, array of mid means this. Sorry. Now this is mid, right? Now 56 is equal to 23. No, it's not. If array of mid is greater than x, if array of mid is greater than x, यानी कि 50, if 56 is greater than 23, is it? Yes, it's true. End is equal to mid minus 1. End is this. Now, do you see now the search space is just this? So initially the search space was this, then it was half, and then it is again half. Okay. So earlier it contained 10 elements, then it contained 5 elements, then it contained 2 elements. Okay. Right. So what we are doing? 10, then 5. So you see how the search space is reducing by half. So that is why it is called binary search. Okay. So now beginning is this, end is this. Okay. So now again, while beginning is less than or equal to end, 5 is less than or equal to 6, the loop continues. Mid is equal to beginning plus end by 2. 6 of 5, 11. 11 by 2 is 5. So mid is equal to 5. Okay. Now mid is equal to 5, and if array of mid is equal to x, now this is mid. Okay. Array of mid, what is this? 23. Now 23 is equal to 23. True. This is true. Return mid. Return mid. This mid is what? 5. Now 5 will be returned. So 23 is present at index 5. This is returned. Right. So our algorithm ends there. Right. So this is how the search works. Okay. Let's say we'll see one more example. Let's say our array is 2, 6, 8, 10, and we are looking for 11. We are looking for 11. Okay. We are looking for 11. Okay. So it's 0, 1, 2, 3, 4. Okay. So beginning is 0. Beginning is 0, end is 5, and x is 11. Okay. Now beginning is less than or equal to end, 0 is less than or equal to 5. Mid is equal to beginning plus end by 2. 0 plus 4 by 2. Okay. So mid is equal to 2. Now mid is this, beginning is this, and end is this. Okay. Now mid is equal to big plus n by 2, 8. Now if array of mid equal to x, 8, is 8 equal to 11? No, it's not. Then else if array of mid is greater than x, is 8 greater than 11? Array of mid is what? 8. 8 is greater than 11? No, it's not. Then beginning is equal to, then this condition doesn't work. Then else beginning is equal to mid plus 1. Now beginning is what? Mid plus 1. So you see what is happening here. Now if the element is smaller than x, right? If the element is smaller, like 8 is smaller than 11, right? So what it is saying, go in the right half, right? And if this element is bigger, if middle element is bigger, then it will say go to the left half. So what happened here? It compared 8 with 11, right? So is 8 greater than 11? No, it's not. 8 is smaller than 11. 8 is smaller than 11 means this element, we know this is in the middle, right? Now what will happen? This is in the middle. So we want to look for a greater element. We are looking for 11. We are looking for greater element where it will be on the right side. If it's the array is sorted in ascending order, where it will be in the right side. That's why we push the subspace to right. That what it is doing in the every iteration, it is just seeing the middle element, and depending on the middle element, if it is greater or smaller, it will either search in left half or right half. Since our middle element is smaller than x, what it is doing, it is telling the it is telling it to go search in the right half. Okay. Now we have beginning is 3 and end is 4. That is what we do. Beginning is equal to mid plus 1. What we are doing? If array of mid is greater than x, means if the middle element, let's say it's 14, if it is greater than x, if this is greater than 11, then what can you assume? Let's say middle element is 14, what can you assume? That it should be on the left side. 11 is smaller than 14, right? So it will be on the left side. So what we should do? We should do end is equal to mid minus 1. This is what we are doing. End is equal to mid minus 1 means search in this half. Otherwise search in that half, right? So this is how the algorithm works. Now let's say we are here. 3 plus 4, 7 by 2 is 3. Okay, 7 by 2 is 3. Now then mid is equal to 3. Right? If array of mid is equal to 11, is 10 greater than 11? Sorry, 10 equal to 11? No, it's not. If array of mid is greater than x, 10 is greater than x? No, it's not. So if 10 we see and we are looking for 11, then where it should be on the right side, then what we should do? End is equal, beginning is equal to mid plus 1. That is what we are doing here. What condition we are encountering here is 10 is not greater than 11. Okay, that's why what we are doing, beginning is equal to mid plus 1. Beginning is equal to mid plus 1. Now beginning is here, right? Because 10 we are seeing, now where should be 11? In the right side, right? So beginning we increased. So beginning is equal to mid plus 1. Now again, is beginning less than equal to end, right? Yes, 4 is less than equal to 4. So mid is equal to big plus end by 2. So 4 plus 4 by 2 is 4. Now if array of mid equal to x, array of mid, now mid was again this. Now if array of mid is equal to x, is this equal to x? No, it's not. If array of mid is greater than x, array of mid is greater than x, yes. If you see 12 and you are looking for 11, 12 in an array and you are looking for 11, then what will you say? That 11 will be on the left side if it is sorted in ascending order, right? So now what it is doing, array of mid is greater than x, yes. So end is equal to mid minus 1, go in the left side. Now end is this. Okay, I know it's very confusing. But end is this at this point, beginning is this and mid is this. Now beginning is, while beginning is less than end, now beginning is 4 and end is 3. 4 is not less than equal to 3, so the loop exists, returns minus 1, which is right because it is not present in the array, right? So this is how the binary search works. So if you look carefully, this is what I told you, right? If you look carefully, what it does is it compares it to the middle element. It compares the particular value to the middle element. Let's say initially what was there, this was the mid, right, initially. So it will compare it to the middle element, the value to the middle element. What it does is it compares the value to the middle element, and if the middle element is bigger, it is bigger. Assume this we have 48. Then where would be 23 in the array if this is 48? Just think about it. If we have 48 here, it's a sorted array. Where will be 23? Left hand side, right? So what we did, end is equal to, end is equal to mid minus 1, right? And if this is not the case, like this is the case, right? 16. So what we do, if this is 16, this is less than 23, right? If 16 is in an array and we are looking for 23, where should it be? On the right side. So what we do, beginning is equal to mid plus 1. So this is what it does in every iteration. What it does is it reduces the search space by half. Like it looks at the middle element. Say here in the first iteration we looked at 23 and 16. 16 we are looking at. 16 is not equal to 23, right? So 16 is less than 23. Then where will 23? In this side, right hand side. So what it did, beginning is equal to mid plus 1 it did, and now the search space is this. Then in the next time search space becomes this. So this is what it keeps doing as it goes on comparing the middle element with the value to be searched. So this is how the binary search works. So now let's come to this point. Why is it only applicable for sorted arrays? Why is it applicable for sorted arrays? Let's say I have, because only if the array is sorted, then you can be sure of the element would lie on the left or it would lie on the right, right? Let's say 2, 5, 8, 12, 16. Since it is sorted, you can say that since this is 16 and we are looking for 23, it will be on the right side, right? That's why you do beginning is equal to mid plus 1. If you know that the array is not sorted, then 23, we are not sure that 23 can be here only, it can be here also. It can be anywhere in the array if it is not sorted. Let's say if we have an array 8, 5, 1, 2, 6, right? Now, if I apply binary search on this, what will happen? If I say 0 plus 4 by 2, 2. This is middle element. Let's say we are looking for 8. So it will say middle element is less than 8, right? So it will be on the right side, but that we can't be sure of because the array is not sorted, right? So because the array, if the array is not sorted, we can never be sure of whether the element will lie on the left or the right. That's why we cannot reduce the search space, right? That's why we only use binary search. We can only use binary search on sorted arrays. Talking about the next point. Okay. Talking about the next point, I'll tell you. First, let me derive the complexity of this. Should I have rubbed it? Okay, 10, 5, 2, you remember, right? 10 and 5 and 2, the search space first. Now let's analyze the time complexity, right? So time complexity of the algorithm and this is an iterative algorithm. Time complexity of an iterative algorithm is the number of times the loop has run. So how many times this loop has run? While beginning is less than equal to n times, right? This is the number of times this loop has run. And inside the loop there is some constant activity going on, comparison, setting some variables, that's it. This part is constant. So the time complexity is time complexity of this, how many times this runs, right? So how many times you think will this run? Okay, let's see. So 10 we had, then we had 5, then we had 2, right? So what it does is in every iteration it reduces the search space by half, right? So beginning is less than equal to n. So earlier beginning was n, search space is n, let's say. In the next iteration, the search space becomes n by 2. Why? Because we are comparing it to the middle element and then we are pushing the search space either to the left or to the right. Either we go with searching in left half or right half, right? And then again if I pass it n by 2, then you saw 10, from 10 it went to 5 and then 2 and then 1 it will go. Alright, so it is going on decreasing n by 2, n by 4, n by 8 plus so on. Till what point we go? Till 1. Okay, so search space, how many times this loop runs? It runs this times, these many times, okay, this many times. Let's say this is k times. Let's say these many times the loop runs. So why am I saying like this is, let's say the search space is n now. First the search space was n, then in the next time beginning and end. What is the size of beginning? So beginning and end, initially the size was n, then it became n by 2, then it became n by 4 and so on. That's what, right? So what is the, how much time it will take? N by 2, then first n, then n by 2, n by 4, n by so on till 1. Till 1 it goes, right? Where it starts at n, then it goes n by 2, then it goes n by 4 and then it goes to till what? 1. Let's say if it is more, not 10 elements, this is less search space. If I say more, then it will take more steps to reach 1. So till 1. Now what is the pattern? If you look at the pattern, this is n, this is n by 2, n by 4, n by 8. If you look clearly, it is n by 2 power k. Let's say in the first iteration, n by 2 power 0, what is 1? N by 2 power 1, n by 2 power 2, n by 2 power 3, n by 2 power. So here what it will be, if this is k times, what it will be? N by 2 power k. N by 2 power 0, 2 power 1, 2 power 2, 2 power 3 and so on till 2 power k. Till 2 power k becomes, till this becomes 1. If you have read about time complexities, right? Then n by 2 power k till what? 1. K times this is running, right? Now we need to find out k. So what is 1 in the form of n by 2 power k form? K is the number of times the loop has run, right? Now n is equal to 2 power k. Let's take log on both sides. This is 1, k is equal to log. So this loop runs log n times and these steps are constant. So what is the time complexity order of log? What is the worst case, average case time complexity? Again, log n. And what is the best case time complexity order of n? Okay, so this is the time complexity of a binary search algorithm, which is significantly lower than linear search. Okay, now let's talk about why is it only applicable to the data structures that are random accesses. Let's say if the data structure is not random access, then let's say we have linked list. We have linked list. 1, 2, 3. Okay, this is very small linked list, but let's say. So if we are accessing mid, we calculate mid, let's say somehow we know n. The funny part is, in order to know n also, we need to iterate through the entire list. Okay, so there only the time complexity becomes n. But let's say, for example, even if that's not the case, we know the size of linked list, let's say we know n. And then we say beginning plus end is less than, beginning plus n by 2 we do. Let's say n by 2 we do 0, 1, let's say. And we are trying to access this element, right? Here it is a very small list, so it can be accessed in constant time, actually the middle element. But let's say we have 10 elements, let's say. 1, 2, 3, 4. I know it's very bad, but please bear with me. I hope you can understand. Okay. Let's say there are 10 elements. Now 0 plus 9 by 2. What is it? 4. To access the fourth element, we cannot access it directly. Like we access an array of mid, we cannot access it in that easy. Why is it possible here? Constant access, because array is stored as a contiguous memory locations. Here it is not the case. So in order to reach here, 0, 1, 2, 3, 4, let's say here, we have to again go from here. 1, 2, 3. So we are going from to the middle element. Let's say n is the size and we are going to the middle element. To go to the middle element only will require n by 2 iterations. Why? How do we traverse this? While temp not equal to null, temp is equal to temp to next. How many times it will run? N by 2 times in the first one. So this time complexity of log n, it has no use there because we have already reached n by 2. So that's why we cannot use it in data structures that are not random access. So in order for us to be able to use binary search, the data structure needs to be a random access data structure. So mostly it is used for arrays. So yeah, I think with that we have almost come to the end of this video, and I hope you could understand what I taught and you are able to learn about binary search. If you do, then please don't forget to press the like button so that this video gets more audience, reaches to the right people, and they can also learn. And subscribe to this channel if you haven't already, it means a lot. And press the bell notification so that you get notified every time I put up a new video. And I'll see you in my next one. Bye.